Okay, hi everyone. I'm not sure if I'm streaming yet. Let me just double check. Yep, okay, can you guys hear me? Okay. So we'll be starting in around 5 minutes. So I'll give you guys a quick break and grab something to eat and drink, and we'll be continuing on with eigenvalues, eigenvectors, and probability. Yep, so I'll be right back. Okay, so just in the interest of time, I think we might get started now. So we're starting off with eigenvalues and eigenvectors. So first thing you want to do is go through the definition. So let A be an n by n matrix with scalar lambda and be a non-zero vector in F. Okay, so if by multiplying the matrix A to the vector V, we obtain a scalar of the same vector, then we can say that lambda is an eigenvalue of A and V is a corresponding eigenvector of A. Right, so just to give a kind of geometric interpretation of what they actually are, if you look at the diagram down below, eigenvectors of A are vectors which point in the same or opposite direction when you multiply by the matrix A. Right, so if you look at vector V2 in the first and second graph, you can see that it's essentially a scalar of the same vector, right? But it's just pointing in a different direction because, again, the scalar is a negative, right? And it's the same thing for V1 as well. And eigenvalues are the ratio of lengths in between A, V, and V. Right, so it's basically what they are geometrically. So if you guys weren't too sure about what these vectors were, and yeah. But the main part of this course is how to compute eigenvalues and eigenvectors. Right, so first thing to note is that the equation AV, so A times your vector V equals to scalar lambda times V, it can be rewritten as A minus lambda I times your vector V is equal to 0, right? Which has a non-zero solution V if and only if your determinant A minus lambda times your identity matrix I is equal to 0. Okay, so how you go about computing eigenvalues and, okay, I will speak a little bit slower, sorry. So how you go about computing eigenvalues is that you work out the determinant of A minus lambda I and you make it equal to 0, and what you get is a characteristic polynomial of degree n in terms of lambda. All right, hopefully you guys know how to calculate determinants, but if not, we'll be going through an example anyway. So once you get your characteristic polynomial, you can solve it and can find values of lambda, which are your eigenvalues. Right? And from there, when you sub in lambda into this equation here, you can actually solve for your eigenvectors. So that's essentially how you compute eigenvalues and eigenvectors. Just something extra on the side here is something that we call an eigenspace. So an eigenspace is a set of vectors V such that this condition holds true, right? So I think this is extra, so I'm not sure if it was in your lecture notes, but a proof of this is by subspace theorem, which you guys went through in, I believe, chapter 1. And you can also use the fact that this set of vectors is equal to the kernel of A minus lambda I, which from chapter 7, you know that all kernels of a matrix are also vector spaces. Right, so again, this is extra, and if you want more proof of that, you can always check out the course notes as well. Okay. And for eigenvalues and eigenvectors, there are two really important theorems that I think you guys should remember. So the first one is the existence of an eigenvalue, right? So an n by n matrix has exactly n eigenvalues if you count all real and complex eigenvalues, and they're also counted according to their multiplicity. Okay, so how this generally works, I'll give you a sketch proof, is that when you work out the determinant and you make it equal to 0, right, you have an nth degree polynomial. And when you consider this polynomial, if these two conditions up here are satisfied, then that means it has exactly n roots, right? If the polynomial has exactly n roots, then that means there are exactly n eigenvalues. Okay, so on these slides, a lot of the proofs are omitted, so you can always check them out in your course notes as well, right? So I'll just give you like a sketch proof of how we find what it basically means. Okay, so that's the first theorem. The second theorem is the independence of eigenvectors. So this theorem states that if a matrix A has different eigenvalues for each corresponding eigenvector, then these eigenvectors are linearly independent. Okay, so this is a really important theorem that we'll be using in an example that's coming up later as well. So if you do take away anything from this seminar, please remember these two theorems. Yeah. Okay, so moving on to diagonalization, this is also a pretty important part of this section. So given A is an n by n matrix with n linearly independent eigenvectors, and this is really important, right? There exists an invertible matrix M and diagonal matrix D such that A is equal to M times D times M inverse, right? And the main thing in this definition is that the eigenvalues make up the diagonal entries of D, and your eigenvectors are the columns of M. Right, so this is the main part. Okay, and this brings me on to theorem 3, which is diagonalization of matrices. So A is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so again, the proof is in your notes, but the main point that I want to address is that if your eigenvectors are linearly independent, right, that means your columns of M must be linearly independent columns, right? And we know that for M to be invertible, its columns must be linearly independent, right? So from there, we can also say that if M is invertible, that means we can use this formula here. So this formula would apply essentially, and we can say that A is diagonalizable as well. So that's kind of how this theorem ties in with the definition. Right, so again, lots of concepts, but we'll just go through an example really quickly. This is a really typical example in both 1231 and 1241, and it's just finding the eigenvalues and eigenvectors. Right, so you're given a matrix A, and part 1 says to find the eigenvalues and its corresponding eigenvectors. Right, so again, setting the determinant, which is the determinant of A minus lambda I, setting that to 0, we have our characteristic equation here. So up here is just how we find out the determinant, right? And once we set it equal to 0, we can solve this polynomial and we have 2 values of lambda. These are our eigenvalues, right? To find the corresponding eigenvectors, you just sub in lambda equals to -3 into this equation here, and this is what we obtain right here. You can actually write this as a system of linear equations as shown here. And the good thing about eigenvectors is that these linear equations are always really easy to row reduce, right? You always get essentially a 0 row at the bottom, and it's always easy to find your vectors from here. Right, so again, you have v2 is equal to t and v1 equals to -3 onto t. Right, these are the two components of your vector v, so just subbing that in here, you have your eigenvector, which is -3, 2, for your corresponding eigenvalue, -3. Right, so it's pretty systematic. I'm trying to find eigenvalues and eigenvectors. So similarly for lambda equals to 2, you do the exact same thing. And like I said, row reducing is really simple and you have your eigenvector right here. Okay, so hopefully you guys are okay with this. I'll just talk about question 2 right now. So it says to find diagonal matrix D and matrix M such that D is equal to M inverse times A times M. Now this here is just taking D as subject in our definition before, right? So don't be too alarmed if it looks different, it's just taking D as subject. So we essentially just need to find a diagonal matrix, right? And we know that the diagonal entries of this matrix are your eigenvalues, so -3 and 2. And again, M is an invertible matrix with columns that are the eigenvectors of A. So this is the first eigenvector and the second eigenvector that we found. Right, so for this question, all you had to do was just state the two matrices. Right, so hopefully pretty simple. Okay, so the second application is powers of matrices. So essentially what we do with this section is that sometimes you're given a problem where you need to find, say, a to the power of 5, a matrix to the power of a pretty large number, and it's really tedious to keep multiplying the same matrix over and over again. So we have something that's called powers of matrices using your invertible matrix M and your diagonal matrix D. Right, so basically, a to the k is equal to m times d times m inverse, and this whole thing is multiplied k times. And what happens is that your m inverse here and your m actually cancel out. They multiply to 1, and it happens for all of these cases. So in the end, what you're left with is just d to the power of k, and then your m at the beginning and your m inverse at the end, right? And the reason why we do this is because, again, we know the matrices D and M, and it's really easy to calculate the inverse of matrix M. And d to the power of k is you're essentially just taking the diagonal entries to the power of k, right? This is a 2 by 2 case. If it was a 3 by 3 case, then your third entry would also be to the power of k as well. Okay, so just a little bit more theory. So a corollary to theorem 2 is that matrices without repeated eigenvalues are diagonalizable. Right, so remember theorem 2 was the independence of eigenvectors. This theorem stated that if all eigenvectors were different, then, so if all eigenvalues were different, then the eigenvectors are linearly independent. So what follows from that is that if A is an n by n matrix with n different eigenvalues, that means A must be diagonalizable. Right, so this logic is just outlined here. So what we do is, essentially each eigenvalue has a corresponding eigenvector. These eigenvectors must be independent according to theorem 2, right? And we know that according to theorem 3, if they are independent, that means A is diagonalizable. Right, this may seem like very, I guess, obvious to you guys, but it's just how this logic kind of works. Okay, but I do want to point out a really important thing here, which is the converse of theorem 2 and the corollary above. So the converse of theorem 2 is that if eigenvectors are linearly independent, then all eigenvalues are different. Now this is actually false. So I'm pretty sure you've seen in examples in a lecture or problem set where you'll find that eigenvectors that belong to the same eigenvalue can actually be linearly independent, right? So this theorem works one way, but when you state the converse, it actually isn't true. So just be careful in the exam if you're told to use a theorem. Don't get confused with your logic, right? So like I said, independent eigenvectors can have the same eigenvalue. Okay, and of course the corollary also follows on from that as well. So a diagonalizable matrix A can have repeated eigenvalues. Okay, so moving on to an example. This one is from the 1231 paper, so it's a little bit more theory involved, but I do think it is pretty interesting. So you're given a matrix A. The first question says that given eigenvalues 1, 2, and 3, explain why A is diagonalizable. Okay, so like I said, make sure you do remember your theorems. We're going to use theorem 2 and 3. So since all 3 eigenvalues are different, that means the eigenvectors are independent, right? So this is using theorem 2. And we also know that A is diagonalizable if and only if A has 3 independent eigenvectors, right? And this is also just by theorem 3. So it's always a good idea to remember these theorems so you can state them in your exam. Okay, so question 2 says to find an eigenvector for the eigenvalue 3. So again, pretty systematic. You just essentially sub in lambda equals to 3 into this equation, and this time we have a 3 by 3 system of linear equations, so a little bit more fiddly, but again, when you row reduce, it should be pretty simple to work out, and you have your, and you have your eigenvector 1, 2, and 2 that corresponds to eigenvalue 3. Yeah, so question 3. This is where it gets a little bit more, I guess, 1, 2, 4, 1 type of questions. So there should be an equal sign here. Let D equal to this diagonal matrix right here. And you know f of x is equal to this polynomial. And here it says show that f of D is equal to the 0 matrix. Okay, so I guess the most obvious thing to do is sub in D into your polynomial equation. So once you sub in your diagonal matrix, you can actually just take the diagonal entries to the power of 3 for this here, and again to the power of 2, and just leaving that as it is, and your identity matrix. So once you sub everything in, you have this here, and essentially you just add all the entries up, and you find that it is actually the 0 matrix. Right, so it's really important to remember that you can take the diagonal entries of the matrix to the power of 3, right, for diagonal matrix D, because it will save you a lot of time, essentially. Okay, So for question 4, it says, hence prove that f of A is equal to the 0 matrix. Okay, remember what A is? A is this matrix here. So like I said, we're going to use the fact that A is diagonalizable. Right, so what you can do, you can sub in A straight away and try and multiply out all your matrices, but we try and avoid that in this course because it's really fiddly and you also might get careless mistakes along the way. So because A is diagonalizable, right, we're going to sub in A is equal to M times D times M inverse. Right, subbing that in, we have this equation here, and we can actually simplify it to this here, right? Because remember, M times M inverse, when you multiply them together, it cancels out anyway, so you're just left with these here. Right, and I've just moved the constant inside the bracket just so it makes it easier for the next step where we factorize out M and M inverse, and in the middle here is your polynomial f of d. Right, and from part 3, we know that f of d is equal to 0, so this here, f of A, is just equal to the 0 matrix. Yeah. Okay, and finally, question 5 says to compute A inverse as a linear combination of A squared, A, and I. Okay, so f of A, again, this time you can just sub in A as it is equal to this equation here, and we want A inverse, A squared, A, and I. So I guess the intuitive thing to do here is to take I as subject, your identity matrix, and you can multiply the inverse to that, because once you do that, you can actually just get this equation here in terms of A squared, A, and your identity matrix. And that's essentially it for this question. Okay. So next thing we have is solving systems of differential equations. So this is another application of eigenvalues and eigenvectors. So let me just see. So this proposition states that given an n by n matrix A, your vector function y is equal to e to the power of lambda t times v is a non-zero solution of the equation dy on dt is equal to your matrix A times your vector y. Right, so this is a solution if and only if A has eigenvalue lambda and eigenvector v. Okay, so I guess you guys all know from calculus that the general solution is essentially just a sum of your solutions, each multiplied with some constant. I have alpha 1 up to alpha n here. Right. So again, it might seem a little bit confusing, but we'll just go through an example right now. So these are two examples. First one is a first order ODE. You're asked to solve this system of linear equations subject to initial conditions stated below. Okay, so this system here can be rewritten as dy on dt is equal to ay, where y is your vector here, and A is actually your coefficient matrix. So if you look back at the question, the coefficients of these two equations are 6, 2, -1, and 1. So this is actually just your coefficient matrix, and if that's a little bit unclear, you can always try and multiply out AY, and you can see that it actually is the case, right? But I believe in the exam, you can just state that it's the coefficient matrix straight away. Okay, so from here, we want to find the eigenvalues and the eigenvectors. Hopefully, you guys are okay with this right now. So I've just skipped some steps. So again, eigenvalues are 2 and 5, and you row reduce and you find the eigenvectors are these two here. Right, so you have two solutions essentially to your system. Okay, so that means the general solution is if you combine them and you have your constant C and D, it's given down here. And with this question, we're not done yet because we are given initial conditions, which means we are told to solve for our constants C and D. Okay, so to do that, you just sub in your initial conditions and you have simultaneous equations, and you find that C is equal to -3 and D is equal to -1. So therefore, your solutions are these two here. So y1 is just your first component of your y vector, and again, y2 is the second component. Yeah. So the thing with this section is that I haven't seen a lot of questions in past exams on solving differential equations with eigenvectors. So as long as you guys get the general gist of how we essentially get the coefficient matrix, and you just do your eigenvectors, eigenvalue calculations, and you should be okay. Okay, but the tricky question is actually the higher order ODEs, where you're told to solve this equation here, right? So this is a second order ODE. So what we do here is we essentially want to try and convert this equation into a system of first order equations with two or more unknowns, right? So y1 and y2. So what we do is first we let y1 is equal to y, and y2 is equal to dy on dt, right? So that means by the first derivative of y1 is just y2, right? Because dy on dt is y2, and the derivative of y2 is essentially the second derivative of y. If we go back to our question, we have our second derivative here. So if you take that as subject, you have 24y plus 2 dy on dt, right? And we know that dy on dt is y2 and y is just y1, which is how we convert our second order ODE into these two equations here. Okay. So once we have our two equations, everything else is just like we did before. This is written as dy on dt equals to ay, where a is your coefficient matrix, 0, 1, 24, 2, right? So just be careful here that this is y2, so it would be your second column that has the 1 at the top, yeah. So just be careful when you write your matrix out. And once you solve this, you have eigenvalues and eigenvectors listed down below. And again, that means your general solution is just your constant times your first solution times plus a constant times your second solution, where C and D are again constants. Yeah. So just to note here though, we let y1 equal to y. So when we want to find the solution, which is just y itself, we're actually just looking at the first component of our vector, y1, which is just c e to the power of 6t plus d e to the power of negative 4t. Should be a t here. Sorry about that. Yeah. So once you get up to this step, that's when you've essentially answered your question. Okay. So hopefully you guys are okay with this, and we'll move on to probability and statistics. I just want to mention though, I'm not sure if you guys have covered Markov chains in 1231, but we didn't cover it today just because it is a little bit too complicated and very long to explain for 1231 as well. So and it's also very rarely comes up in exams anyway. But if you guys do want any help with that, again, feel free to ask, and I might add in a little bit of that in the supplementary materials anyway. Okay, so we're going to move on to probability and statistics. This section of the course, I believe it was taught really quickly. It was in like the last 2 weeks, and it was also really rushed, and there's also quite a lot of content to go through. So bear with me guys, and hopefully it'll be okay. So the beginning of the course had a lot of set theory, which I haven't covered here just because it's more of like supplementary material, so it like helps with your understanding of probability, but it's not necessarily tested much in the exam anyway. So we're just going to go straight onto probability. So the definition is given here. So it's a function p where p of s maps to a real number r. Now this definition here, try not to focus too much on it, as long as you understand what a probability is, essentially, right? So the first dot point here just states that probability must be between 0 and 1, which is fairly self-explanatory. Okay, the second dot point is stating that essentially the probability of no event happening is 0. That means something will always happen, an event will always occur for probability. Okay, and the second equation here is essentially stating that a probability of, probability of something amongst everything will happen. So that just means that something will definitely happen. So the probability of that will always be 1. Okay. And the third dot point here is stating that the probability of event A or event B happening is equal to probability of A plus the probability of B for all disjoint sets A, B, that's a subset of S. Now, disjoint here just means that these two events, A and B, are mutually exclusive, so that just means that one event happening won't affect the outcome of another event, right? Which is why we can just add them, but that's usually not the case. Usually, we always have to subtract off the intersection. So subtract off the probability of both A and B happening simultaneously. So this equation here is a lot more useful and is something that you should remember as well. Okay, so again, some more fundamental rules. First one is, I'm sure you guys all know, is the complement rule. And this third dot point here is essentially saying that if A is a subset of B, that means that A is a special case of B, right? That means the probability of something that's a special case, that's a subset of a general case, will always be less than the probability of a general case, right? So if you think about it, hopefully that makes more sense. So the probability of a special case will always be less than the probability of a general case, right? And the last dot point here is just stating that probability sum will always equal to 1. So what we focus on mainly in this section, probability, is something called conditional probability. Okay, so this one is essentially saying that the probability of event A happening, given that the event B has already occurred, is equal to the probability of the intersection over probability of B. Okay, so this vertical line here is just another way of saying given. So A given B. Okay, so again, it's really helpful to draw tree diagrams. So I actually suggest drawing tree diagrams in your exam, just so you can keep track of each of the outcomes and each of the probabilities. It's a lot easier. So what this definition is saying is, given B has occurred, so your first branch would be whether B has occurred or hasn't occurred. Find the probability of A occurring. So from here, you would branch off into A occurring or not occurring. So, A or A complement, and then again A or A complement for the second branch. So that's how your tree diagram works. And in a lot of questions, they generally just ask you to find the condition, which is probability, more over the outcome. So don't worry too much about this outcome at the end, the A intersection B, A complement intersection B, and so on. Right? So you should usually just find the probability. Okay. So 3 important rules in this section. First one is called the multiplication rule. Now this one is basically just rearranging your definition, right? So A intersection B is equal to A, the probability of A given B times probability of B. And again, it works the other way as well. Right? It's literally just a fancy way of using your tree diagram. You just multiply the branches. Okay. The total probability rule is I guess a special equation that's used for taking cases, right? So you're essentially looking at all the cases where the event A would have occurred, right? If you look at your tree diagram, you see A occurs in the first branch and also in the third branch here. So you're multiplying the branches and you're adding them up. You're essentially just taking cases. And finally, the Bayes rule. This one's the most important rule in this course, I reckon. So it's useful if you want to find, I guess, B given A. So if the conditions have been swapped and you want to find a probability of B given that A has occurred instead, then you use this rule here. Okay, so yes, do try and remember this. I guess it's probably the most important formula in this section. We're going through an example now. This one was from last year's paper, and it's essentially just drawing a tree diagram. So you're given this information about A and B, right? And let's give you a second to note that down. And this is a very dodgy tree diagram. I'm so sorry for this, but this is essentially what the tree diagram looks like. So probability of B occurring is P, so complement is 1 minus P, and I've just labeled all the branches down here and the outcomes on the side. Okay, so question 2 says to find P. Okay, so if I want to find P, that means I need to use probability of B somehow, right? So what we can use is actually the total probability rule. So again, using this formula, the probability of event A happening would be if I multiplied P times 0.3, right? And I get the first outcome here at the top. And also if I add the probability of B not occurring and then A occurring after that would be, if you multiply it would be the outcome number 3, right, when you go down the list. So if you write out the formula here, this is what you get, and you actually just get this equation here, right? And going back to the question, you'll see that you haven't used this fact here where the probability of A is equal to 0.2. So if you just sub that in, you actually can solve for P. You have 0.5 as your answer. Okay, a more difficult example. This one was from, I believe, the 1231 paper, but 1231, I think you guys should know this as well. So you have 2 urns. One contains 3 red balls and 4 blue balls, and the second contains 4 red balls and 2 blue balls, right? So a ball is drawn at random from the first urn and it's placed in the second one. Okay, the first question says, what is the probability that the ball drawn from urn 2 is blue? Okay, so again, I've drawn a tree diagram. Please always draw a tree diagram. It's so useful. And the first question is actually just your total probability rule again. So the probability of drawing a blue ball from urn 2 is where you have the case B2. Right? You can see by multiplying the branches, I have this equation right here. So I have 3 on 7 times 2 on 7, and I use plus 4 on 7 times by 3 on 7, which is how I get my probability. So I guess it's really confusing sometimes when you look at the actual formula, but when you actually go through your tree diagram, it's pretty self-explanatory. So I think you guys should be okay with this. The second question says that given the ball drawn from urn 2 is red, what is the probability that the ball transferred was blue? So this time your conditions have been swapped. So you want to find B1 given R2, essentially, right? And again, always use your Bayes rule, and you can just sub in into the formula here, and you'll find that your answer is 16 on 31. Right, so I'm just going to stress this again. Please remember the Bayes rule. It's very important. Okay. And the third part is actually pretty interesting. It says, let A be the event that the ball drawn from urn 1 is blue, and B be the event the ball drawn from urn 2 is blue. Are A and B statistically independent? The answer is no, because if you think about it, if I take a ball from urn 1 and I place it in urn 2, I'm changing how many balls there are in urn 2. I'm also changing the number of each color, essentially, of the balls in urn 2, right? So my sample space is changed, so that means they're not statistically independent, right? And you can see it here as well. If I take the probability of the intersection of A and B, it's not equal to just multiplying the separate probabilities. Right, so this is why they are not statistically independent. Right, and I have a definition of this right on the next page. It's called mutual independence. So these two events are mutually independent if this equation here holds true. Right, and it's similar to saying that the probability of A is equal to the probability of A given B, because the event B has nothing to do with event A if they are independent. Right, and again, it's the same thing for the B case. Yeah, so I think that's basically all for probability. The most important part was the conditional probability part. So if you guys can understand some of the questions that we did, then you guys should be fine. Okay, now it just gets a little bit more content heavy. So we're starting statistics now. First thing we want to cover is a random variable. So what is a random variable? This is the official definition. It's very complicated looking, but you don't actually need to know the definition, just what it means. Right? So I have an example down here. So essentially what a random variable is that this function capital X, it assigns each event in your sample space S a corresponding number, smaller case x. Right? So in your example, if you have 2 dice and your function x is summing the two dice values when you roll them. That means your elements in your set would be, say, 2, 2, 1, 2, 5, 6, 3, 4, right? The two values on your two dice. Right, so that means your sample space, your Sx here, would be all the possible sums of your dice values. And you're essentially assigning these to a number, lowercase x. That's essentially what a random variable is. So yeah, you don't need to know the actual definition, just what it means, essentially. Okay, so a discrete variable here, a random variable is discrete if its image is countable. Right, so this just means that you can list the numbers where that it's assigned to. So you can list, so there'd be like natural numbers or numbers from like 0 to 6, for example. So that's basically what discrete is. Okay, next thing we have is a cumulative distribution function. So the cumulative distribution function is this function f of x where it's equal to the probability of your variable as less than or equal to your assigned variable, small case x. So let me just explain that a little bit clearer. So it's the probability that this variable, capital X, takes okay, sorry, let me think this through. Okay, so it's the probability that your variable takes it's a probability that the variable takes values less than or equal to x. Okay, essentially. Right, so just remember this formula here, and it should be good for cumulative distribution function. Okay, so I'm just going to go through some of the properties down here. So the first one here just states that if b is greater than or equal to a, then f of b would be greater than or equal to f of a. And the reason for that is f of b is taking more values that are less than or equal to b compared to f of a, which means that f of b is, I guess, summing up more values that are compared to f of a, which is why it's always going to be greater than f of a, right, given that this inequality is true, right? And this just means that f is also non-decreasing. Okay, the second dot point here states that if x is in between, takes values in between the interval a and b, essentially you can write it as f of b minus f of a, essentially. And here just note that it's strictly greater than a. Okay, and the last dot point here, don't worry too much about it. You don't actually need to focus on this too much. I guess I cover it really briefly in the lectures. Just know that it's a thing, it exists. Yeah. Okay. So moving on from that, we have probability distribution. So this is just a description of the probabilities of all events associated with x, right? And it's denoted by this here. So p of your variable is equal to a number, essentially, where the range of x is given by x1, x2, and so on. Okay, so the conditions for a probability distribution to exist, essentially, is that your probability has to be greater than or equal to 0 for all k. Now, this is quite obvious because it is a probability. And the second case here is that the sum of your probabilities has to equal to 1. So you guys should know these two from high school anyway. So it's just another way of writing them down here. Okay, so the a note is that the cumulative distribution function for a discrete random variable x is given below. So it's essentially just the sum of your probabilities where k is less than or equal to x. Okay, so moving on to expected value. The expected value is just the average, so the mean. So you're looking at where all your values, where do they generally lie? Where do they generally accumulate is where your mean would be. Okay, so we have a theorem for this. Oh, sorry, this is like the, I guess the formula. So you're essentially just multiplying the outcome, so xk, by your probability of the outcome happening, which is pk. And you're summing them all up. Okay, so moving on, we have a theorem. This is the expected value of a function of a random variable. So this theorem is important if the question asks you to find the expected value of, say, x squared or x cubed, or some function of x, so not just x by itself, right? You essentially just multiply the probability by the function of the outcome. Yeah, and for the variance is looking at how spread out x is from the mean, right? So that's what the definition is, and here is the formula. So I do recommend just remembering this formula below. It's a lot easier to calculate than this one above here, but yeah. And I'm sure you guys know standard deviation is the square root of your variance. Yeah. So the good thing about probability and statistics is that a lot of the questions, they don't ask you to write out the proof, they just ask you to calculate, right? So before we move on to an example, we have one more theorem, which is the scaling and shifting of a random variable. So again, I haven't seen this come up a lot in your past exams, but it is useful to remember them. So this is what happens when you have, I guess, a constant times x plus a constant on the side. Yeah, so this is what happens to your expected value, your variance, and your standard deviation. Okay. So moving on to an example, this is a very typical example in 1231 and 1241. So it says, let x be a discrete random variable with the following probability distribution. And you're also given that your expected value is 3.3. Part 1 says to find the missing probabilities p and q, and part 2 says to just calculate the variance. Okay, so part 1, remember for probability distributions, we know that the sum has to always equal to 1. Right, so when you sum up all of these values here and let it equal to 1, you have this equation. P plus Q is equal to 0.5. Right, and we're also given that the expected value is 3.3. So again, just working out your expected value using this formula here, you're multiplying the outcome with the probability and you're summing them all up. So 1 times 0.1, 2 times 0.3, 3 times 0.1, 4 times P, and 5 times Q, and make that equal to 3.3. Okay, and then from here you have two equations, you can solve them simultaneously and you get P and Q. Okay, so once you have P and Q, you can work out your variance just by using this equation here. You have, so this part here is the expected value of x squared, and then minusing off the expected value of x all squared, and you have 2.01. Okay, so it's moving on to more definitions. I'm sorry, this part is very content heavy, but hopefully you guys are okay with this. So first thing we have is something called a Bernoulli trial or process. So a Bernoulli trial is an experiment with two possible outcomes. You either succeed or you fail, right? So we usually denote success as P and fail as 1 minus P, right? And a Bernoulli process is essentially just identical trials, a sequence of identical trials where they are all independent of each other, right? And here the number of successes in a Bernoulli trial is given by this formula below, where again P is your probability of success, and N is the number of trials, and K is, I guess, the number of successful trials. Yeah, and I just want to note that Q here is 1 minus P. Yeah, so I think in a lot of theory notes, they just put 1 minus P here, so it should be. Okay, so this brings me to binomial distribution. Binomial distribution is essentially you're just asked to find the probability of k successes given n trials and success probability p. Right, you'll see that it is very similar to Bernoulli trials because it is essentially just leading on from that. Right, so the binomial distribution is a probability distribution, and sometimes you are asked to prove that in the exam. So if you're asked to prove that something is a probability distribution, you just prove that pk is greater than or equal to 0, and that the sum of all the probabilities is equal to 1. Okay. And down here, we just have the expected value and the variance. So expected value of a binomial distribution is just NP, and the variance is NPQ. So again, the proof of these, they should be in your lecture notes, but a lot of questions just ask you to try and find the expected value and variance anyway. Okay, so a geometric distribution is a little bit different. So this one is looking at how many times you essentially fail before you succeed. So it's looking at trying to calculate the probability of your first success, right? And usually your first success here is given by the kth trial, and it's only if your first k-1 trials or failed. Yeah, and it's given by this formula up here. So again, it forms a probability distribution, and down here you have your expected value and your variance. Okay. Okay, so just a quick overview of sign tests. So I do believe this one you guys did cover in your lecture. So sign tests are used to decide whether a comparison between two sets of figures or a standard and a set of figures is assumed to be just chance, pure luck, right? Or if there's evidence of a difference between the two. So if I look at the example below, this table just shows the marks of 15 students in their algebra and calculus test, right? So for example, the first student scored a 7 in algebra and a 4 in calculus, and so on. So how we do these questions is, first, you ignore the students who essentially got the same mark for both algebra and calculus, because they won't be helping our analysis anyway. So you ignore the second student and the 14th student, right? So out of the remaining 13 students, we can see that if you count them, 10 students did better in algebra than in calculus, right? So if you base it on these figures, you can say that we're not going to say that students did better in calculus than algebra, right? So we'll just be focusing on the algebra case. So if I let my students, a number of students who did better at algebra be x, right? We can say that it is a binomial distribution with 13 trials, and the probability of success is a half, because we are assuming that it is pure luck at this stage, right? So if I find the probability of obtaining these results that are more extreme than what we have here, so the number of students is greater than or equal to 10 who did better at algebra, and we can calculate it here using your binomial distribution, right? You can find that it's actually 0.0461, right? And since this is actually less than 5%, it's really unlikely to say that the difference was just pure luck, right? So that just means that the students are actually better than algebra than calculus. It wasn't just a half chance that they were better at algebra or at calculus. Right, so in this course, we say that any probability, any percentage that's less than 5% would be very unlikely, and that it was that wasn't pure luck, essentially. Yeah. Okay. So now we're going to move on to continuous random variables. So what a continuous random variable is that it takes in real numbers on an interval, right? So this variable takes in all possible values that cover an interval of a real line, right? So we're not looking at just discrete integer values anymore. Okay, so the definition of a probability density function would be this down here. So it's equal to the derivative of your cumulative distribution function if f is differentiable at x. If it's not, we're looking at the limit, right? So the intuition behind this probability density function is that you're looking at the area under this function that is used to calculate the probability, right? Which is why when we integrate the probability density function, it gives you your cumulative distribution function. Okay, so these are just more properties, and you can see that it looks similar to your discrete random variable properties, right? It's essentially the same thing, except that instead of a sum, you have an integral sign, right? And the reason for that is because you're looking at continuous random variables. Right, so again, your probability density function is always greater than or equal to 0. When you integrate it, you get your cumulative distribution function, and when you integrate from negative infinite to infinite, which is essentially just summing up all your probabilities, you get 1, right? And finally, you have, if you're integrating in between an interval, then you have this equation right here, right? Okay, and if you guys can understand the discrete random variable and how it works with expected value, then for the continuous random variable, it should be pretty simple as well. So instead of the summing notation, you have the integral notation. So you're looking at integral between negative infinite to infinite of x fx dx for the expected value. And again, if it's a function, you're looking at g of x, where y is equal to g of x. Right, and again, for the scaling and shifting, it's similar to discrete random variables, so nothing changes in that aspect. Okay, so now we're looking at an example. So this one was from the 1231 paper. Again, you should probably expect something like this to pop up on your exam. It's a very frequently asked question. So it just says, if you're given the probability density function below, and you're expected to find either the value of k, or you'll be asked to find the cumulative distribution function, right? So in this question, you're asked to find the value of k, and you're also asked to evaluate the expected value and the variance. I just have a 1241 example listed below. So if you check out the 2016 paper, it's also on probability distribution function, but it is a little bit different. So if you want, I guess, a taste of what 1241 would be like, then try and attempt that question. So for part 1, we want to find the value of k. So since it is a probability density function, we know that the integral between negative infinite and infinite of this function would equal to 1. Right, so just integrating this and moving back to your question, you can see that you're given bounds of 0 and 3. So integrating, you have this value here, and you can actually find out your k. So k is equal to 109. So question 2 was to find the expected value and also the variance. So first we want to find the expected value, again using your formula. So the integral between negative infinite and infinite of x fx. So again, integrating this, and you have 9 on 4. For your variance, again use the easier formula to compute, and you can actually just find this below. So expected value of x squared would be the integral of x squared f of x, and again working that out, you get 27 on 5. And then when you subtract off the square of your expected value, you have this value here. Okay, so these questions are pretty, I guess the working out is the same for these type of questions. Okay, so moving on to standardization. So standardization is more focused for normal distribution, which we'll go through in a second. So what you're doing is you're essentially modifying your random variable x to obtain this variable x such that your expected value is now 0 and your variance is now 1. Right, and again, the reason why we do this is for our normal distribution, which is right now. Okay, so for your normal distribution, it's a continuous random variable with this probability density function. Now, you're looking at it, and I know it looks really complicated, which is why we don't actually integrate this function at all, because it's quite hard. So what we do is we have a table of values which you can refer to actually find out what your standard normal probability is. Right? So it's written as this below, and again, standard normal distribution has mean 0 and variance 1. Okay, so how do we calculate normal probabilities? So to find a normal probability, it involves, again, integrating probability density function, but we can't do that. So we usually just reduce to the normal standard distribution using this change of variable, which we went through before. Okay, so once we reduce this, as you can see here, I subtract off the mean and divide by the standard deviation at the bottom. And by doing that, I get this value on the right-hand side of my inequality. Now, this value on the right-hand side of my inequality can be found on the table of values. Right? So hopefully you guys know how to read the table of values. You essentially just match the number with the probability in the center of the table. Yeah. So I'll just go through an example right now, how you would use this. So this one was from the paper 2 years ago in the 1231 paper, yeah. So for this question, it says that suppose that the final mark of a student in 1131 is normally distributed with mean 59 and standard deviation 7.44. Okay, so given that the pass mark is 50, we want to find a percentage of students that are expected to pass. Okay, so first we let x be the mark of a student in this course, and we're given that, again, mean is 59 and standard deviation is 7.44. Okay, so we want to find probability of a student getting a mark that's greater than or equal to 50, so passing. Right, so again, we standardize this random variable and we get z is greater than or equal to negative 1.21. Right, and in your standard table of normal probabilities, all the probabilities are less than or equal to a number, right? So we always want to use the complement rule here, and you get this value here, and this is just found from our table, and we get our final probability, which is 88.69%. Okay. I just have a question that's a little bit harder. So this time, it says that the time in seconds of a group of athletes running 400 meters is approximately normally distributed with mean 48.7 and variance 1.9. Okay, so estimate the value of t such that the fastest 2% of these athletes achieve a time of t seconds or better. Okay, so in this question, we're given mean is 48.7, and this here should actually be the square root. So I'm sorry about that. It should be square root of 1.9. And the question here asks us to estimate a value of t such that the fastest 2% achieve a time of t seconds or better, right? So we want our athletes to achieve a time t or better, so x is greater than or equal to t, and we know that this is 2%. Right, so this time in our question, what we're doing is we want to solve for t, right? So again, we use our standard normal distribution, which is z, and we minus off our mean and the square root of our variance, right? And again, using the complement rule, we have this here, and this is equal to 0.02, right? So hence, this value here is equal to 0.98, and if you look at our table of standard normal probabilities, we have z is less than or equal to 2.06 is equal to 0.98, right? So that means that this fraction here on the right-hand side of our inequality has to equal 2.06, right? Which is how we find the value for t. So this question, you're using the same concepts, but you're solving for a different value. Right? Okay. And finally, we have normal approximation to the binomial distribution. Now, I was told that you guys went through this really quickly in your lecture, so I'll just be going through it a bit more. So normal distributions are used to approximate the binomial distribution for very large values of n, right? So these distributions are used to model experiments that involve a large number of identical and independent trials with several possible outcomes. So if you see the graphs below, you can see that the bell curve is your normal distribution and everything else is your binomial distribution, right? And you can see how it approximates below. Okay, so when we use this concept, there is something that we need to cover, which is continuity correction. So continuity correction is just an adjustment that is made when a continuous distribution is used to approximate a discrete distribution. Right, so if you look at our table below, you can see that we're altering our values just by either adding 0.5 or subtracting 0.5, right? And this is because discrete random variables, they can only take specific values, right? But continuous variables take values within an interval that's around these specific values, right? And because we can take an interval instead of just one specific value, this actually increases our accuracy, which is why we have continuity correction, right? It's to reduce any rounding errors. Okay, so Just a note here, for continuous random variables, the less than or the less than or equal to sign are actually the same, because for these variables you can't actually make them equal to any specific value, because remember, the probability of obtaining a specific value, if all your variables are an interval on a real line, is actually just 0. Which is why in some questions they just use these two, I guess, interchangeably. Yeah. So we're going through one more example. So this one is looking at binomial distribution, and you'll also use using the normal approximation. So Denver attempted an online examination where he answered 50 multiple choice questions, and in each question there's 5 choices with 1 correct answer, and let x be the random variable counting the number of questions he guessed correctly. Alright, so from the question, you know it's a probability distribution with 50 trials and success probability 1 on 5, right? Which means your failure probability is 4 on 5. Okay, so remember expected value for a binomial distribution is n times p. So this one is 50 times 1 on 5, which is 10. And again, your variance is npq. And again, that is just 8. Okay, so for this question, you can just state the expected value and variance straight away. Okay, so for question 2, it says use a normal approximation to the binomial distribution to find a probability that Denver correctly guessed 12 questions or more. So we want x, the probability of x is greater than or equal to 12, right? And this is where we use our continuity correction here. So going back to the table, if we want x is greater than or equal to a value c, then we actually, when we use a normal approximation, we subtract 0.5 from this value, right? Because, again, it decreases our accuracy, and it's essentially the same thing in the end. Right, so if I subtract off 0.5, I get y is greater than or equal to 11.5. And again, I haven't changed the sign here because for continuous random variables, it doesn't matter if we have strictly less than or equal to. Okay, so here, just subtracting off our mean, which is 10, and our standard deviation, square root of 8, we have this value right here. And again, if we want to refer to our table of values, we need the complement, and you just take the 1 minus p of z is, probability of z is less than or equal to 0.53, and referring to your table, you have this probability here. Right, so 29.81% chance that Denver correctly guesses 12 or more questions. Okay, so we are a little bit short on time. And if you're from 1231, thank you for listening, and I hope you guys do well in your exam. We just have one more thing, which is exponential distribution. It's more for the 1241 case. So I'll just go through this really quickly. This is the definition for exponential distribution. What this distribution does is that it looks at, it's essentially used to model waiting times where the event can occur at any time, so it's not specific to integer values. So for example, in this question, you're on a highway and cars pass at an average rate of 5 cars per minute. So assume that the duration of time between 2 cars is an exponential distribution. That just means that during this time, you don't know when the car is going to pass, so you don't know the specific integer value, but you just know the, I guess, the interval of time where it will pass, which is why we use the exponential distribution. Okay, so I'll just go through this example really quickly. First question says, on average, how many seconds elapse between 2 successive cars? Right? Since the average rate is 5 cars per minute, that means there is roughly 12 seconds between each car. Okay. The second question says to find the probability that after a car passes by, the next car will pass within the next 30 seconds. Right? So let t be the time between successive cars. So from part 1, we know that the expected value, which is, I guess, the average time it takes for a car to pass, is 12 seconds. Right? So rearranging this, we have a parameter lambda, which we need for our definition here. Right? So that means we can approximate, we can look at the exponential distribution with respect to the parameter lambda, which is 1 on 12. Okay, so how these questions generally work is that you use your cumulative distribution function, t. And to do that, we integrate your density function, which is given in a definition, and you actually get 1 minus e to the power of negative lambda t, where t is greater than 0. So for this question, if you want a car to pass within the next 30 seconds, you're looking at t is less than or equal to 30, right? So all you do in this case is you sub in 30 into this equation for t, and you know your lambda is 1 on 12, and you can work out the probability right here. Okay, and again for the last question, it's the same concept, but this time the car will not pass for at least another 20 seconds. So you're looking at the times where should be a t, where t is greater than or equal to 20, right? And again, using your complement rule, you can work it out, and you can actually find that this is equal to approximately 18.89%. Okay. I'm sorry that was quite rushed at the end, but hopefully you guys are feeling a little bit more confident with your exams. And thank you for listening, guys. And yeah, if you guys have any questions, please feel free to ask anyone in MathSoc. So just hop onto our Discord anytime. And also, these slides will be up by tomorrow afternoon, should be. Yeah. Thank you, guys.